This is House Planning Help episode 182. Hi there, I'm Ben Adam Smith, and this is the podcast for you if you're interested in self-build, because I'm exploring what houses we should be building in the 21st century and trying to break down the major roadblocks that may get in our way. Coming up in this session, my guest is Justin Broadbent from ISO Energy, and we discuss using watercourses to generate electricity and extract heat. First up though, maybe you haven't listened to this podcast before and you're wondering what it's all about. You've just dipped in episode 182, perhaps specifically because you're interested in watercourses. Well, that's fair enough. I thought I'd bring you up to speed that for nearly 5 years now, I've been attempting to tackle my own project, and I've been learning from people in the trade and also those self-builders who've been there and done it, just trying to get some information from them. And that's what these podcasts have been about, learning as we go along. Hopefully you can share in that learning journey as well. One thing that I have done is put together a 10-part email course of some of the top things that I feel I've learned. This is specifically to do with ecological design. So if you are new to the podcast, perhaps just starting your journey, then I'd encourage you to check that out if you're not going to go into the back catalogue of podcasts. So you can find that at houseplanninghelp.com/tips. So Justin Broadbent returns to the podcast. It's been a while, a couple of years. We chatted to him in episode 17 about ground source heat pumps. He was using one to heat his period dwelling. This time round, we're looking at watercourses and the best ways to extract heat or to generate electricity. So I started by asking Justin almost about the history of this renewable source, and I wondered whether it was first to be harnessed, or could it be wind?
I should think probably in the UK, I'm not an expert on it, but I would actually think probably watercourses were there before wind, for the simple reason that there's much more energy in water because of the density of water than wind. So when you're making basic mechanical objects, it's easier to see how you could use a water wheel rather than a wind turbine. Having said that, possibly in places like Holland, where windmills were the main form of energy, they don't have, although they have water because it's very flat, but there's no flow in the water because it's basically just ponding. I should think in the UK, certainly all the early mills were all driven by water. Grain grinding was done by wind, but certainly the mills for the early industrial revolution was all done through water because of the amount of power in the water.
And where do you choose along a watercourse, or how do you assess when it's right to start extracting energy?
Well, it depends on what sort of energy you're trying to extract. Any water can be used for energy extraction. A large pond, can be used for extracting heat. The amount of heat they can extract out of it is relative to the size of the pond and the heat load required. If the pond is flowing, that is that there's a flow in and a flow out, then the energy is effectively being replaced all the time, in which case you can take more. If you have a stream, then the energy is being replaced very, very fast, so you can take more energy. That energy is really heat. You have a constant known 7 to 12 degrees temperature in a flowing river, or a pond can actually get much higher than that, but we have a constant, and that constant is constantly being replaced, so you can extract loads of heat out of it. With regards to electricity, you need what in industry terms is called either flow or head, and head is like a waterfall, a mountain stream or something like that has head, and between the top of the stream and the bottom of the stream gives you the calculation how much energy you can take out of it. To extract electricity, you need head and or volume, preferably both.
Is the heat version the simplest to begin with? Should we go down that route first?
It's the simplest and the most likely to be worthwhile, especially in the southern parts of England. If we're in Wales or Scotland, then no, hydro looks good. In southern England, generating electricity out of thing is rare. You've got to find a mill stream. You've got to find an old mill. That's where they position them. If you just have a small stream running through your garden, as in fact I do, really the only thing you can probably do is extract heat out of it.
And how would we do that then? What are these devices?
Okay, there are a number of different ways. The simplest way, if you take a pond, it's the simplest. A pond is fairly slow running water. You simply install some sort of heat extraction mechanism, which is often coils of pipe, plastic pipe really, which we circulate through a heat exchanger and extract heat out of it. If you have slightly flowing water, then there are items called energy blades, which are effectively stainless steel radiators, if you can imagine a radiator, a bank of 4 or 5 of them made of stainless steel so they don't rust. And in a flowing stream, you can extract an enormous amount of energy out of it, because almost whatever you take out, as long as you don't actually freeze the water, 2 seconds later, there's new fresh water coming down the stream. So we have huge manor houses using hundreds of thousands of kilowatts hours a year out of streams, just by putting in a bank of 20 stainless steel radiators, basically.
And there isn't a case of affecting wildlife or anything downstream?
No. I mean, relatively speaking, the amount of energy you're taking out of a stream is very, very small because of the volumes involved. Out of a pond, there is the opportunity, if you like, to cool the temperature of the pond. And yes, it probably does affect wildlife slightly, but frankly, in England, in Great Britain, let's say, it's the same fish that live in the south of England as live in the Highlands of Scotland. So they just probably think that you've moved them up north after we've cooled the pond slightly. You mentioned that you've got a watercourse and you're not doing anything. Is there a reason? I think this period property that you own is heated by a ground source heat pump. Yeah. Is there a reason you chose one over the other? Only decades of, we started 11, 12 years ago, and in those days, ground source was what we sort of understood. As the years have gone by, we've developed how to extract heat neatly out of water. We do actually have one system. We have a gym in the industrial yard, and that is heated via a pond using an energy blade, actually.
So there's not much in it, really, when it comes down to it.
No,
it's just a choice.
If I was starting all over again, I would probably choose the river rather than the ground, simply because it's cheaper to use a stream. The problem with the river that we have here is that it suffers a lot from flash flooding. There's a lot of development going on in the area, and the amount of flooding is getting worse. And as such, it makes it difficult to control what you're actually putting in the river. But if I was starting again, I'd probably use the river. It's the more efficient way of doing things.
From a cost perspective, is there anything to consider when you're weighing up your options like you were mentioning?
If you're fortunate enough to have a stream, it means that you can just, as it were, plunk an energy blade in the stream. Euphemistically, I mean, it might be a bit more complicated than that, but you plunk an energy blade in the stream and it costs you a couple of £1,000s to install it, and Bob's your uncle, you have an energy source. To do the same thing with the ground, you might have to dig, off the top of my head, 500 metres of trenching, a metre deep, a metre wide, put a load of plastic pipe in the ground, all the glycol that goes with it, etc. And instead of costing £2,000 or £3,000, it's cost you £5,000 or £6,000. So that's the main driving force, and it won't be quite as efficient. The river will be more efficient because you can cool the ground, but you can't cool a river.
Maintenance?
There's both ways. There's very little maintenance as such. It's a fairly static. It is a radiator.
How might it break or come to the end of its life cycle?
Well, these things are built of stainless steel, so they have quite a long life cycle. I mean, you can imagine that maybe a tree trunk could come down the river. It's not impossible. Obviously, when we're doing these things, we build them with guards in the front, but it's not impossible that something could come down and take it out, as it were. You'd probably be able to find it bit downstream and pick it up and bring it back, but that is an issue. In the olden days, before we had these energy blades, we used to use plastic pipe. That was a bigger issue because often that can get dragged down. In fact, it's not strong enough, and so we stopped doing it after a while.
So what would it look like then if we're going down this route? Just explain perhaps if there's an example that you've done recently for a customer that we can show some photos of this particular way and what process you went through to completion.
Yeah. I mean, different customers do it in different ways, and I can give you some photographs for your website or whatever to show different ways of doing it. But I mean, the simplest way is literally if you have a small stream in the bottom of your garden, you just put the energy blade in the stream and dig a small trench back to your heat pump, and it's up and running. Other people go to extremes of making it a feature. I have a couple of clients who actually diverted part of their stream and dug a canal and concreted it in and have a walkway over the top of it so that they can actually demonstrate to people how they're heating their house or their swimming pool or whatever. And it's quite nice. It's quite nice for us as well, obviously, as a company that does do these things, but you don't have to go to that extent.
I quite like that. So has that pretty much given us an overview of this extracting heat? Is there anything else we need to be aware of, or?
No, if you have the right spot and you have the right watercourse, then it is fantastic. I mean, it's just the only way to do it. If you don't, then you can't do it. It's as simple as that. There's no halfway. It either works or it doesn't.
Is there any way we could tell ourselves, or do we need to get someone who knows what they're talking about?
You get someone in. We have, as a company, 50 man years worth of experience in this now. You don't learn by our mistake or learn by our mistakes. I mean, we made plenty of them along the way.
All right, let's move on then to more hydro now. We're saying that it has to have this fall of water, a flow of water. Is it one or the other, or are you looking for both?
Well, ideally, you're looking for both. I mean, so if you have a big mountain river, fantastic, and you see people building dams. You go to the Alps, you go to Scotland, you go to Wales, they build small dams, and then you see the pipe coming down the mountain, and that's a traditional hydro system, and it's all about volume of water creating weight in the pipe, which means that you can run a turbine at the bottom of it. The greater the head, which is the technical term for the fall, for the drop, the greater the head, the more power you can generate. So if we think about the south of England, there aren't that many apart from the North and the South Downs, and you'd be unlikely to get planning permission to do anything on those. So you have to get planning permission going down this route? It's an area of outstanding natural beauty, absolutely you do, yes. Yeah.
But on a normal river?
To dam it, yes you do. Yeah, to put an energy blade in the water, no you don't. It's no different to building a small pier or something like that, and it's easily removable. But to dam a stream, yes you do in this country need the Environment Agency or river authorities, it used to be, permission.
Is it always a turbine that's quite a severe piece of kit?
No, we were just discussing in the south of England, you don't have very many mountain streams. And so what you do is if you look at where the old mills were built, it tends to be a hill stream, and they would dam it slightly and put a traditional water wheel in place, and that would then drive the machinery of the mill. Those are typically good areas. I mean, they built them where they built them because they were good places to build them, as it were.
I was going to say that this might be one of the key giveaways, yes, that you're on an old mill site, and you've actually got a good case study that maybe we can dig into.
We have 3 or 4 mills that we've converted to do exactly this. And, if you're fortunate enough to have bought a mill, then yes, it's great. Or if you're next to a mill on the same mill stream or something like that, then there's lots that we can do for you, probably. In those cases, traditional turbines aren't any use because you don't have enough head, but you have lots of volume in the stream. So, in an ideal world, you have head and volume, and then you can build a traditional turbine. If you don't have the head, then you have to have even more volume, and you still have to have some drop. You still have to have, let's say, 6 feet, 2 meters of drop is enough as long as you've got a few thousand liters a second going through the stream. In which case, the best way of doing it then is what's called an Archimedes screw. And Archimedes originally invented his screw to actually send water uphill when they were sending water around in Rome and Greece and they used the Archimedes principle to actually pump the water in the first place. Nowadays, we tend to mainly use it in the opposite direction, using the flow of the river or the stream to turn the turbine. And on the end of the screw, there's an electrical generator, basically, that generates electricity.
And it's quite effective. If you had this next to a house, you're going to be able to get a fair amount back, obviously dependent on the size of the river.
If you're fortunate enough to have the right spot, it is incredibly effective. I have clients who now are generating 15, 20 kilowatts of electricity an hour, which is far, far more than you need for any single house. 24 hours a day, 365 days a year, and effectively, apart from a little bit of maintenance, it'll go on forever. And it's a very good, wonderful way of doing things. We should be doing more of it in this country.
What happens with that surplus?
it goes back into the, assuming you're on the grid, which most people are in the electricity grid. If you have electricity coming into your house, then we can send it back the other way. They basically sell it back to the electricity companies. So it's a bit like if you have PV panels, photovoltaic panels on your roof, they might produce a few kilowatts. Well, an Archimedes screw should be able to generate tens of kilowatts, much more efficient.
And there were some incentives. Are they still going? Or?
Oh, yes, yeah. The same feed-in tariff that pays you to generate electricity with photovoltaic cells pays you to generate electricity with a Archimedes screw. Of course, with PV panels, they only work, between the hours of daylight. So, and if the sun's shining, they work well. If the sun's not shining, they don't work so well. With a river-driven, and it tends to be that you're generating electricity during the day in the summer, when you need the electricity the least. With an Archimedes screw flowing through a river, you tend to generate slightly more power in the winter because the rivers are higher, and it runs 24 hours a day, 365 days a year, so you always have the power when you need it.
And what would wear out or need that maintenance? Because it's obviously got a lot going through it all the time.
Yeah, the screws themselves are fairly maintenance-free. The bearings, of course, will one day go, and the gearbox at the top needs maintenance, but it's not a huge amount. I mean, it's no more than maintaining it's a fairly basic system in reality. It's heavy but basic.
And I imagine you need quite a big space to put it in. Do they vary a lot in size, or tend to, for this sort of purpose, be a set size?
As with all these things, size matters, I'm afraid. So the smaller the size of system, the less return on investment you get. So if you have a stream that's, let's say, 2 meters across and half a meter deep, then that's a good size. And out of that, you'll probably get something like 10, 15, 20 kilowatts of energy, depending on the fall that you have. If you have a stream that's only half a meter across and 250 mil deep, you might get 5 kilowatts out of it. But because of the amount of civil engineering and the cost of making these things, actually, there's not much difference in the cost between the two. But the return on investment on a system that's producing 20 kilowatts is obviously 4 times greater than one that's producing 5 kilowatts. And so it is rare that as a company we want to get involved with things that are much less than 20 kilowatts, because you spend an awful lot of time and effort in getting permissions of this, and then the costs mount up, and suddenly you found that it's all going to cost £150,000 and you're only going to make $5,000 a year out of it. Doesn't pay back.
And do you almost divert the river a bit? Because, I mean, how are you going, when the river's flowing, you don't want to be building in the middle of this?
Yeah, that's why we always look for mill houses, because the mill stream is already been diverted off the main river. And so it's a nice controlled environment to work with. Even if you are... but whatever happens, you always have to worry about the environment, obviously, that we're all here trying to do things for the environment. And so we don't want to be blocking the river so that fish and eels and animals can't get by. So this always has to be just a part of the stream, if you like. You can't just say, well, I'm going to block this stream forevermore, because, well, we did that in the Victorian times, and half the rivers became devoid of fish and salmon and eels and things like that. So we're trying, and the Environment Agency are trying to rectify that situation. So nowadays you can't block a stream completely. You always have to have a fish pass or something.
What is a fish pass?
A fish pass is exactly as it's called. It's a way of giving the fish a route upstream without having to go through the mechanism.
How do they avoid it? How do they not say, wow, there's something very interesting down there, I'm sure of it?
Yeah. We put a sign up for them to read. Fish this way, eels that way, and water that way. A fish pass, or a fish ladder, as they're often called as well, is basically, it looks a bit like a maze of slow little drops that they can easily swim up and rest in the middle, etc. So they're quite expensive to actually put in, funny. And that's why, again, we go for the bigger sites, because you might find that the Archimedes screw itself costs you £15,000 for a 5 kilowatt one, and it costs, let's say, £60,000 for a 20 kilowatt one. That's just the screw. But then the civil engineering is going to cost you another £20,000 either way. And the fish pass is going to cost you £30,000, and then getting the planning permission and the consultant's time is going to cost you another £40,000. And so the whole thing's add up. And actually, that's why size matters at the end of the day, because you need to have something that's going to generate a decent return on investment. Otherwise, it doesn't happen. Lots of people start off with the best of intentions, but actually, at the end of the day, if you don't get a return on your investment, it's not hardly worth doing.
Is there anything else we need to think about with this hydro side of things?
I don't think so. I mean, I think you if you have a stream running through your garden or beside your house or whatever, then it's certainly worth investigating. What can I do to use the stream? How can I use the stream to the best of the ability? And the two ways are really either generating electricity and or generating heat. If you can do both, then it's fantastic, because you use the electricity to run a heat pump, let's say, which is using the water, the flowing stream, to extract the heat out of, and you suddenly find that you've not only got a house that's completely free to heat and cook and use electricity, but you're probably going to get a lot of government subsidies to support the construction of the whole system in the first place.
And I imagine a lot of this is about payback. Yes, you've got all that money to begin with. If you can just stomach that for a few years, how long do you think some of the systems you've done have taken to repay?
With government subsidies, how they are at the moment, or the incentives, we ought to call them rather than subsidies or grants, because you have to do the work and then claim back the incentive. Normally, the incentives of generating electricity go on for 20 years. So you once you're in, you get paid for the next 20 years, which is extraordinary. For the heat, it's normally about 7 years. Heat, assuming everything being even, you probably get your money back between 3 to 5 years after the cost of installation. Normally, you'll get about 12 to 20% return on investment for the initial capital cost over a 7-year period. And after that, you've got hugely reduced running costs for forevermore. So, it's definitely worth doing, so long as the government grants are out there.
Justin, it's always good to catch up with you. Thank you very much for the information today.
My pleasure.
Head online to take a look at the show notes that accompany this session, houseplanninghelp.com/182. You can review all the main information again, some good photos as well. That will really help you get your head around the blades and the Archimedes screw. If you've got a comment or you'd like to ask a question, scroll down to the bottom of the show notes. And of course, as ever, we will link you across. Today it's ISO Energy, their website, and also where you can find them on Twitter. houseplanninghelp.com/182. Let's conclude today with a hub update. I just thought I'd let you know of the latest content that we're prepping up as we speak. Very close to releasing a video that looks at the next stage of Buckinghamshire Passive House. This is our current in-depth case study. And they're up to the stage where they're installing a steel. And this steel actually has very little to do with the structure of the building, but more to be able to get a large living dining space. And so that goes into the building. There's some air tightness taping. Of course, there's a lot of air tightness taping, very important part of the job. This is the first time we see it, because below ground in the basement, it was all concrete, and that's quite airtight. And we have our first little bit of insulation. This is actually, I don't know whether this would be considered the least important. Of course, it's all important, but this is sheep's wool insulation that goes around the window frame. So there are 4 different types of insulation that are used in the PH15 system. So that's the latest video. Also, we're course creating too. Current one, looking at designing a house, perhaps from the perspective you're wanting to work with an architect. What will you need to do? What will you need to prepare? What are the checklists? All of these things coming together in our latest course. If you're not a Hub member, well, we've got the community side as well. We'd encourage you to get yourself on the VIP early bird list. And when we open up the doors, which will be fairly soon actually, houseplanninghelp.com/join. That's it for today. Thank you for being there. Really appreciate your company. The House Planning Help podcast is produced by Regen Media, content that matters.